That's why the countdown, and I don't start till the exact moment, and I'll stop when the course is over. This is Math 425, complex analysis. I'm Steve Bell, Math Department. There's my office, my phone number. That's my home page. Everything to know about this course you're going to be able to find on the home page for this class. So I'm not going to have Brightspace is basically to be links to the home page. So that's where you'll find everything you need to know about the class. And so that would be the URL capital M, capital A, 425 off my home page there. That's where you'll find everything. Let's see, I'll show you what that web page looks like. There it is. We'll have a grader who will grade the homework. Sean Nolan. There's his information. The textbook is I like this book a lot. It's a kind of nice in between a pure math kind of proof-based course and engineering calculation kind of course. So it's kind of the right thing. It's the way I like to teach the subject. There's a lot of applications, and so you're learning how to compute with complex numbers and integrals is going to be an important part of the course. And of course, understanding why it all works is what a course like this for math majors is all about. Anyway, it's by Saff and Snyder. There it is on the home page to look it up. Third edition, that's kind of important. Old editions have different homework numbers, etc. So that'll be a mess. So I'll always post my lecture notes after class, and also that if the Boilercast works, when it works, there'll also be a video that looks exactly like what you see here, hopefully with my voice over it, if this microphone works. And so see that it says Aftermath there? If you click on that, you'll find lecture 1 isn't there yet, but it will be when I post it after class, and the video of this lecture should be available. So that's what that'll look like. I got in the habit of doing that during the pandemic, and it seems to be appreciated. If you ever have to miss class for some reason, you'll be able to find a video there. I think you'll have a better experience sitting in class because you can sort of focus and ask questions, etc. But if you ever have to miss, then you'll be able to find the videos there. The first homework is posted there. I'm going to make these due in Brightspace. in Gradescope, which you can get to through Brightspace. And so that'll be due next Thursday at 11:30 p.m. in Gradescope. That looks like a lot of problems, but this first chapter is very introductory, basic facts about complex numbers, etc., that you probably learned in some place, high school maybe, junior high maybe. So it looks like a lot, but those are fairly routine. My grader's only going to grade 5 problems per homework, but I won't tell you which ones because it's important you sit down and do them all. But it's not so important that he grades them all. So that's the first assignment. It's already there, and I'll bloop out assignments as I make them. Question?
Yes. So in the homework assignment, it says lessons 1, 2, and 3, and then it says homework.
Yeah. So today I'm going to talk about lesson 1. Wednesday's 2 and Friday's 3. And lesson 1 is going to cover the first 3 sections of chapter 1. Let's see. There's more syllabus items here and various things you should read on the home page. One thing that would be interesting to you is the grade business. There's a standard statement about grade cutoffs. Those are the standard numbers for Purdue. And of course, since this is a math major course at a senior level, the cutoffs might be lower than that. They won't be high, they'll never go higher, but they might be lower. In fact, they're likely to be lower. So there's going to be a midterm exam. This is all spelled out in that spot. I'll have a midterm exam and a final exam. and the homework. That's the main components of the course. And let's see, so why won't this go down? Huh? So the midterm exam will be 100 points. The homework will scale to 100 points total. And the final exam will be 200 points for a total of 400. And those percentages at the top, I hope this still works. The percentages are just a rough guess about what your grade would be based on those totals. But likely the cutoffs would be lower than those. Any questions about that kind of stuff, course stuff? I'll probably send an email summarizing some of the things I said today. Yeah. Yes, in class midterm. I'll let you know the date for that when I figure it out. Yeah.
Is there a PDF of the syllabus?
Well, no, there isn't, but it's on the home page.
I checked it out, but I would, yeah.
Yeah, I prefer not to print out gobs of junk. But the homework will bloop out one homework assignment at a time. For a senior class like this, I think it makes better sense, so I can modify it in case I think of a better thing to do. Other questions about anything? Well, this is one of my favorite subjects. I mean, this is my favorite subject. I do research in complex analysis in one and several complex variables, and wrote a book about it myself, and so I get a bang out of it. And so I like complex analysis because I can sort of start from scratch. It kind of feels like freshman calculus for a little while, but it very quickly becomes much more interesting and exciting in a lot of ways. So, I mean, if you've been exposed to complex numbers probably starting in junior high when you solved a quadratic equation, and so the thing you were told is you try to solve a polynomial equation like x squared plus 1 equals 0. Of course, there's no real number, so that x squared is equal to minus 1. And so the big idea is you toss in an imaginary number, which is kind of an unfortunate name because all numbers are imaginary. But we toss in a thing, and we call it I. It's just a symbol, and I is a thing such that its square is equal to minus 1. Okay? Well, if you're going to toss in an I, you're also going to need things like 7 times I. And then if you're going to have things like 7 times I, you would also need things like 3 plus 7 times I. And of course, they don't have to be integers or rational. You could have e plus I pi, etc. Makes sense. But then if you think about tossing in more things, for example, an I squared is equal to minus 1, so that wouldn't add anything new. I cubed would be minus I, so that wouldn't add anything new. And so, in fact, when you think about, okay, if I had like 3 plus 4i to the 10th power, you'd multiply that out like a polynomial, and then use the fact that all those powers of I simplify to either being a real number or something times I. So you expand that and play around with it and realize that you can always write things like that in the form real number A plus real number B times I. And that's because you start out with I squared is equal to minus 1, I cubed is equal to minus I to the 4th is equal to plus 1 again, etc. when you expand that polynomial. Okay. Well, that just feels like a game. And it is kind of a game in the beginning, but it's a game that has a sort of very exciting payoff, and quite rapidly. There's a famous theorem of Frobenius, the theorem of Frobenius. I don't know why they never say Frobenius' theorem. Frobenius said whenever you play this game and add finitely many things to the real numbers, there's a very limited amount of new things you can get. So let's see. The famous theorem is any division algorithm. Any division ring, they call it. That's an algebraic thing. Any division ring obtained by adding finitely many things. It's called a finite extension. So I'll say not, but what the heck, sorry. Fix my eraser. Any division ring obtained as a finite extension of R. So here above, I added I, one stupid thing. That's a pretty simple finite extension of R. Well, I could have added more than just I. I could have added other roots of polynomial equations. And I could add finitely many and play the same game. It turns out that here's an algebra word, isomorphic, meaning to either, for example, if I added the square root of 2, that would be the same as R basically. It wouldn't change. So the first possibility, it's isomorphic to R. The second possibility is it's isomorphic to the complex numbers, which are the basic complex numbers you get by adding I. And it turns out there's one more possibility. H, which are the quaternions, you might have heard of them. And nothing else. So in other words, if you play this game, you're going to get, the interesting case is C. And even if you add other things, not just that one stupid thing and call it I, but other roots, the best you can get is that you can get C or the quaternions. Or if you add like square root of 2, you just get R back. Okay. To me, this means that the complex numbers are not imaginary. I don't think they're complex either. I think they're fairly straightforward. Complex in the complex difficult sense. So it means sort of they're things of nature. Yeah, question. A division ring, you can multiply things together and you can find inverses, but you don't know it's a field. The interesting thing about these things is R is a field, C is a field, but the quaternions are not a field. So the fact that C is a field makes it a preferred thing, definitely. Yeah. Anyway, that's an algebra fact. I don't want to dwell on it, but I want to make it feel like the complex numbers are sort of as natural as the real numbers in a lot of ways. Okay, well, I like to think of the complex numbers the way everybody thinks about them, going back to Gauss and the team. Namely, all all the numbers a plus bi such that a and b are real. Okay, if you want to be very formal about it, you can also think of this as being sort of the same as the set of points in the plane, x, y, such that x and y are in real numbers. All right. Then, like you learned in junior high, if you're going to add two complex numbers, z1 plus z2, let's see if we write x1 plus iy1 plus x2 plus iy2. Of course, you learn how to manipulate complex numbers. You add them like vectors. And so you just add the real parts and imaginary parts and get a new complex number. You can think of that in the plane also as adding x1, y1. This is just vector addition. So the addition of complex numbers is just like vector addition. Okay? And so this thing on the right is a very formal way of thinking about this. And then when you multiply complex numbers, let's see, you multiply them like a polynomial. And when you do that, you get x1, x2, and the imaginary parts, when they multiply, you get an I squared. So you get minus y1, y2. That's the real part. And then the imaginary part is x1, y2 plus x2, y1. And of course, I can write out the same thing in this more formal looking thing. x1, y1, multiplying a point in the plane times x2, y2 equals the same thing. I'm not going to write it out again, but you get the analogy there. Anyway, you can make a very formal thing out of that. And the interesting thing is it's not terribly hard to show that you get a field. A field is like the real numbers. You can divide, you can multiply. There's a whole bunch of axioms for fields, which if you had an algebra book, well, I think it's in our book too. I'll let you read it. Anyway, a field, so exciting moment is C is a field. Okay, and so if you're going to talk about a field, you need a zero element. Of course, the zero element is 0 plus 0 times I. And we'll write 0 for that. And the identity element is 1 plus 0 times I. And of course, we'll write 1 for that. Okay, so that would also correspond to the origin in the plane, and this would correspond to the point 1, 0 in the plane. And the interesting thing in the complex number is I, such that I squared equals minus 1. That is 0 plus 1 times I. And of course we write I for that. And that's the point 0, 1 in the plane. Okay. So that C is a field, and the thing that everything is easy to check. All the axioms of the field, of, the commutative laws, the associative laws, etc., etc. tons of laws are all straightforward to check. The interesting thing is that non-zero complex numbers have a multiplicative inverse, and in fact a unique one. Let's see, you learned how to do this in junior high. The multiplicative inverse of the complex number z would be we write 1 over z, and let's say z is x plus iy. Then you learned in junior high to manipulate that. You multiply it by the top and the bottom by the complex conjugate of the denominator. And when you do that, you get x squared plus y squared on the bottom. That's why it's desirable. And so let's see. And on the top, so you get x over x squared plus y squared is the real part, minus y over x squared plus y squared for the imaginary part. Okay. That's how you learn how to do that in junior high. If I was going to kill time here, maybe I would have done this the first time I introduced complex numbers in a high school. A fun exercise, if you think about multiplying two complex numbers together and getting 1, then you can write out x plus iy. Let's say w is equal to u plus iv. And then, of course, you get two linear equations. Let's see, you get u times x minus v times y plus vx plus uy I equals 1. So that's 1 plus 0 times I. And so if you want to find an inverse to, say, z, then this thing needs to be 1, and this thing needs to be 0. Those are two linear equations in, say, the x and the y's. And you can use Kramer's rule to solve them. And when you do that, you would get x equals the determinant of, let's see, the thing that's going to be in the bottom is the determinant of u minus v u. That thing in the bottom is going to be that's going to pop up again and again in the course. Something called the Cauchy-Riemann equation. And that thing in the denominator there is very related to the Cauchy-Riemann equations. We'll see it pop up again later. Anyway, when you do Kramer's rule, let's see, the x, you leave this thing here, and then you put the 1 and the 0 in that column. And of course, you get that it's u over u squared plus v squared. And similarly, when you do the y, you get the same thing you would expect from the junior high method. And what's interesting is that determinant in the bottom is u squared plus v squared. So if that's a non-zero complex number, that determinant is non-zero. And so you would see that the inverse is unique. So of u plus iv, if it's not 0, is unique. That's a very important part of being a field. Okay, so this is the kind of stuff that's kind of tedious to read in the book. I'm going to let you read it. I'm just giving you the highlights and the words. Questions about anything? Let's see, I'm going to set up some standard notation. that everybody agrees on. Let's see. We like to think of complex numbers in the plane, sort of in that dual way of thinking, either as a point, x, y, or as the way Gauss did it. Let's see. That's going to have a name. Let's see, I'll take dot, dot, dot. Here's an x. Here's a y. And so this is z equals x plus iy, which is also the point xy in the complex plane. Okay? That's how we visualize complex numbers. Let's see, there's going to be a point that we'll use quite often called z bar, the conjugate of v. That's x minus iy. So you get that by reflecting about the x-axis. That's the conjugate of z. This red line here is called the modulus of z, and it's that length. That's the square root of x squared plus y squared, and that's called the modulus of z. It's that radius there. I find myself slipping and saying absolute value quite often, but that's different than the absolute value of a real number. It's that radial distance there. So when don't let me do that. In fact, you might find that I tend to write one thing, say another thing, and think a third thing. So if I start flubbing things up, I prefer you catch it and point it out to me so I can fix it in the notes. I very often go back to my office and fix things that I flub up before I post them. So if you ever are suspicious that I flub something up, check the notes on the home page. Let's see, we'll have one more thing in here. This angle is going to be important. That's going to be the argument of z. And of course, that way I drew a picture where sort of theta is the obvious thing, but I could have gone around 2 pi more times before I got to there and get a different theta. So theta is annoying in that it's not unique. Theta is called the argument of z. Let's take the principal argument. In that picture, that's the argument of z, and this is the principal argument of z. And it's the theta in the picture. Let's see, to make theta unique, we would have minus pi is less than theta. Let's see, you've got to think about is less than pi. We want every complex number to have a unique modulus. So over here on the negative real axis, if I go around the positive way, I'd get pi there. If I go around the negative way, I'd get minus pi there. And I got to make a choice. So the traditional thing to do is so that minus 1 will have negative real numbers will have an argument. We let pi win. That's the principal argument. Okay. I'll say more about arguments in a minute. There's a whole bunch of easy facts that I could bore you to death by checking. But I won't. For example, the complex conjugate of a product is the product of the complex conjugates. Just write up both sides and say, sure enough, that's a true fact. Another one is that the complex conjugate of a 1 over z is 1 over the conjugate of z. Oh, some more facts that are fun is z times z conjugate is equal to the modulus of z squared. Easy things to check. Interesting, when you look at that, you can see that 1 over z is equal to z bar over the modulus of z squared. We've already seen that. Okay, so I'm going to a lot of routine stuff to check. Historically, of course, I think somebody in Persia realized how to solve quadratic equations. So let's see, this is what you learned in junior high school. If you have x squared plus bx plus c equals 0, then you look at and say, boy, that'd be nice if that were some kind of a square, then I could take square roots. And you say, well, I see kind of a square here. I see x plus something squared. All right? And what I would need there to make that look more like a square, if I would need b over 2. That would give me x squared plus 2 times b over 2 times x. That would give me the bx part. And then I'd get plus b squared over 4. And that kind of messes things up. So what I have here is a plus c. And to stop from messing that up, I would have to subtract minus b squared over 4. Now I haven't changed anything. And now I have something that looks like a square that maybe I'll be able to take the square root. Okay. And so you learned in junior high that, then the next thing to do is I put that junk on the other side and get b squared over 4 minus c. And I realize, aha, the last thing to do is to take the square root, and then I can solve for x. Of course, it was disturbing to the first people who did this. That thing on the right-hand side could be negative. So if you're trying to get a real number that solves a quadratic equation, but what if the right-hand side is less than 0? Okay, so the first people who messed around with this, they tossed in I, and then suddenly they could solve all quadratic equations. So suddenly, you can solve all quadratic equations. The mind-blowing thing about complex numbers is that just tossing in that one stupid number, suddenly I can solve any polynomial equation. Okay, that's an exciting thing. And that's why complex numbers are exciting. And why they're sort of natural. They're a thing of nature. You can't avoid them, really. If you want to understand real polynomials, you've got to let the variables go complex. So the famous fundamental theorem of algebra tossing in that one stupid number is that given any complex polynomial, polynomial, let's all write it as P of z I'll have a first coefficient, an, that's a complex number, an times z to the n, plus another complex number times z to the n minus 1, plus dot, 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 plus a1 times z down to a constant term, a naught. So let's see, this an better not be 0. And all the other a's are complex numbers. All the a's are complex numbers. Let's see, for the fundamental theorem of algebra to make sense, we need this degree, n is the degree, needs to be bigger than 1. If it were just a constant term, then this wouldn't make any sense. Or it'd be kind of a silly thing to say. So that's, given any polynomial like that, the conclusion is that P of z has a root, or also called a 0, or root, in C. Meaning, a number an R in the complex plane with P of R equals 0. Okay, that's really exciting. And is evidence that you sort of have to add this one stupid number so that suddenly you can solve all complex, all polynomial equations. So those coefficients could be real. And like in the quadratic case, it can happen. You have real coefficients and you need a complex root. But a corollary of this, when you learn the Euclidean algorithm in high school, is that you can factor polynomials. So the P of z factors over C. That's exciting. Even if it was a real thing, you could factor it over C and maybe understand more about the polynomial. And so factoring over C means if you find a root, then you learn from the Euclidean algorithm that you could factor out that root. In fact, when you do that again and again, let's see, we'd factor out the first root. That would be a z minus r1 times a polynomial. Then you'd factor out the next root of that polynomial. And you keep doing that, and every time you do that, the degree goes down by 1. And the last time you do it, a first degree polynomial looks like z minus a root. You can do that n times until you get down. And the constant term has to be that capital A sub capital N when you think about what that constant term could be. So, that gives you a deep understanding of all polynomials. That's all they are. They look like that. Of course, those r's can repeat. So those rn's are complex numbers, and it's important to realize the rn's can repeat. Okay, so far it feels like I'm playing games with algebra. And that's what I've been doing so far. But things got exciting. To understand why the fundamental theorem of algebra is true, Gauss and his buddies resorted to inventing calculus with complex numbers. And that led to a whole bunch of fascinating things and new ways to understand these things. And it's funny that how natural it seemed in the beginning, because it felt like freshman calculus. So here's the exciting thing we're going to do in this class. Calculus with complex numbers. Okay, so let's think about what that might mean. So a difference quotient, when you take a derivative, let's see, I'm going to think about, would look like f of z minus f of a over z minus a. And we'll have to think about, so let's think of these as complex functions, like the polynomials above. Okay? So the f of z is like a polynomial, think of that, if you want to think of a function there. And so I can write out that difference quotient. That's just a complex number. And a complex number is a point in the plane. And if that complex number tends to a point in the plane, as z tends to a, as a point in the plane, then we think of that as the complex derivative. Of f of z at a. Of course, I'm going to write out epsilon delta definitions of these things in the traditional math manner soon. But today I'm just giving you a feeling about it. Let me do an example real quick. Let's take f of z equals z squared. Something very simple. And that difference quotient would be z squared minus a squared over z minus a. And like in freshman calculus, z squared minus a squared is z minus a times z plus a. And then you see, the z minus a's cancel, and that's z plus a. And if I write z as x plus iy, and let that tend to the point a in the complex plane, we see that that tends to 2 times a, as z tends to a. So just like in freshman calculus, in fact, it feels like there's nothing new here, f prime of z is 2z. Or let me write f prime of a is 2a. Just like freshman calculus. So for a while it looks like, oh, this is going to be a similar game to the algebra. You just do it. Feels kind of natural and normal, and you think it's going to feel like freshman calculus. But the next example kind of dashes that expectation. That's right. Maybe I'll use a different. All right. G of z equals z bar. Or in other words, g of x plus iy is equal to x minus iy. Turns out that limit doesn't exist. So, and I'll explain that more in the next few days, is not complex differentiable. So even though it looks like it's, everything is smooth, x and y are very smooth things, it looks like it ought to be infinitely differentiable, but it's not differentiable in this new complex sense. Okay, so something is interesting is happening, and we'll have to think about it harder. Talking about Gauss and Euler and all the people who founded the subject, it was just by playing around that they came up with the complex exponential function in the beginning. And today I'll talk about the complex exponential function by just playing around the way Euler did. We write the complex exponential as 1 plus z plus the Taylor series that you're familiar with. Euler wrote that down and played around with it and realized that the thing you learned for power series back someplace probably is that he did the math, he did the algebra, and realized this rule holds for the complex exponential. E to the x plus iy is e to the x times e to the iy. And e to the iy, when you write it out, is 1 plus I times y plus I times y squared over 2 factorial. And of course, I squared is minus 1. And then we get plus iy cubed over 3 factorial. I cubed is minus I. And so Euler sat down and wrote that out carefully. And when he did that, let's see, the e to the x part sits there in front. And he collected the real parts. Let's see, the real part here would be 1. I squared is minus 1, so that'd be minus y squared over 2 factorial. The next one that would be real would be would be a plus y to the 4th over 4 factorial. Next one would be minus, etc. Those are all the real things. And now the imaginary parts with an I in front of it. We see a y there. The next one would be minus I times y cubed over 3 factorial, etc. The next one would be plus y to the 5th over 5 factorial, and then they would alternate again and be negative. And so Euler was the first one to realize that if the complex exponential was going to make sense, he recognized this as the power series for the sine function, no cosine function. And he recognized this as the power series for the sine function. And so if the complex exponential is going to make sense, it ought to be e to the x times cosine y plus I sine y. And he invented the notation that this is e to the iy. Okay. The complex exponential is the most important function in all of math. And I hope to convince you that over the course of the semester. But today we're just going to define it. So that's the most important function in all of math. And therefore also in science. And so for us in the beginning here, we're going to define the complex exponential in this way. E to the x plus iy is defined to be real part e to the x cosine y, imaginary part e to the x sine y. I'm going to show you that that's complex differentiable, and guess what? Its complex derivative is itself. So the derivative of e to the z is e to the z. And that turns out to be the defining characteristic of the exponential function. It's its own derivative. And in the complex case, it's a complex function that's its own derivative. Okay. So we'll start out making that a definition. I'm going to study it from first properties later, because it's possible, but I wanted to get moving as quickly as possible. Question?
Are we missing an I on the e to the x?
Probably, yeah. Thank you. That's good. You should do that whenever I do that. Other question? Same? Okay, yeah. Let's see.